Hey, right, so I'm happy to meet you all here. It's nice to give a talk on this stuff. Some of you may have seen some versions of this talk. Some of you may have not. To those of you who have, I'm sorry. I'm going to have to recap some of the old stuff just to make sure that people who have not seen anything, that they are on the same page. And towards the end, there's stuff that's really new and a bit raw. So it might be a bit more jumbled than the stuff at the beginning, which has been given many, many times before. So anyways, today I'll be talking about my work on prior networks and specifically a reverse Kl divergence training criterion, which allows prior networks to be trained in a better way, and also which allows them to be used for adversarial attack detection. So, and this is joint work with my professor, Mark Gales. Right, so the structure of this talk is as follows. First, we'll just kind of recap why do we need uncertainties in general. Then we'll recap the sources of uncertainties and Bayesian ensemble methods, which you should all be very well familiar with. And then we'll talk about prior networks and adversarial attack detection. So let's get going. Context. So the scenario we're all operating in is that we have some kind of model, it makes a prediction, and it also gives us some kind of measure of uncertainty in the prediction. And using that measure of uncertainty, we can then take some kind of action. We can, for example, reject the prediction, we can accept the prediction, we can ask for human intervention, we can deploy active learning, we can do many, many things. And in fact, people are always finding new things to do with uncertainty. In general, there's all these applications. There's various forms of threshold-based outlier detection, like misclassification detection, error detection, out-of-domain input detection, adversarial attack detection, active learning, reinforcement learning, and there's many other things which people can use uncertainty for. Later in the talk, I will discuss out-of-distribution input detection and adversarial attack detection. So, yeah, that was the quick overview of this scenario. By the way, if you have any questions, ask away during the talk. But if you have a philosophical discussion with me, or you want to debate and do verbal dueling, let's do that afterwards. Right. Anyways, so source of uncertainty. In general, there's three reasons why we can have uncertainty. One is we have some kind of inherent uncertainty in our data. The classes are overlapping, people have mislabeled some stuff. That's the first case. The second case is we have some input in a region of input space which is sparsely covered with training data. And finally, we have an input in a region which is not covered by the training data whatsoever. Right, and we refer to the first thing as data or aleatoric uncertainty, and the second and third things are data sparsity and out-of-distribution inputs. In fact, the second and third thing are two forms of the same effect, knowledge uncertainty. We have inputs about which we have limited or no knowledge because we don't see these things in training data. And so we are uncertain. So I'll refer to these things as data uncertainty and knowledge uncertainty. Although I believe Bayesians often call these things aleatoric and epistemic uncertainty. So anyways, data uncertainty. So here we have a toy data set with 3 classes. It's all quite simple. We have a green input. We're all happy here. All classes are easily separable. We can make a confident and certain prediction. It's all good. Suddenly, I've made the classes overlap. I've increased the variance of the Gaussian clusters, and now they overlap at the center. In this case, I can't confidently say to which class the green point belongs to. It may be class 2 or maybe class 3. I don't know, because the features in this region have properties which are similar to many different classes. So classes are overlapping. Data uncertainty. A sort of kind of amnesty example. On top, we have handwritten digits 1, 2, and 7, which are written clearly. On the bottom, they're written badly, and therefore we can't really understand what digits are there. 1, 2, or 7. So this is a sort of an easy example. In general, data uncertainty is a form of known unknown. We have data in this region. We know that the classes are overlapping, and we know that we can't make a confident prediction. This can be due to class overlap, like the complexity of classes, or it could be due to a human labeling error, for example, and accumulation of human labeling error. Right. In general, your estimate of data uncertainty is given by the entropy of the true level of data uncertainty is given by the entropy of the true underlying conditional distribution over y conditional on your input x. But obviously, we don't actually have the true distribution. We only have samples from it. So if we train a model using maximum likelihood estimation on this data, then the model will provide then the entropy of the model will be an estimate of data uncertainty. And in general, yeah, we skipped over something. No, we didn't. Anyways, so that was data uncertainty. Is that clear? Any questions at this point? No questions. Cool. Going on. So this is knowledge uncertainty with some input which is really far away from the region of training data. We don't know anything about it. It could be a new class. It could be a weird version of an old class, or maybe the entire input space like wraps around itself in some weird and interesting way, and maybe it's class 1 instead of 3 or something. We don't know. We don't have any data there to tell us anything about that region. A sort of more concrete example is on top left you have MNIST digits from 0 to 9, and let's say we train an MNIST classifier, as we always do for our NIP submissions, and then we expose them to some omniglot data, which is the top right. An omniglot is a data set of characters from many different alphabets. And obviously, MNIST doesn't really tell us anything about omniglot, doesn't tell us about the characters or the classes in omniglot. And therefore, our model, we would like our model to be uncertain in the prediction it's making when it's exposed to omniglot. A less extreme example is if we show it the characters 1 and 7, which don't have a little like hat on the top for 1 or a crossbar for the 7 in training data. And we only see these variations of 1s and 7s. And then in our test data, we have a 1 with a hat and a 7 with a crossbar. And in this case, our model may generalize or our model may not generalize, but we don't know. But like in this case, it's like it could conceivably generalize, as opposed to the top example where it really won't. So yeah. Now, in general, data uncertainty is a form of known unknown. As I've said before, knowledge uncertainty is an unknown unknown. We have no knowledge about some region, and we really can't make any statements about it. Now, why do we care about separating out the sources of uncertainty? It's because the actions we would like to take using our measures of uncertainty may strongly depend on the source. For example, if we're doing active learning, then there is no point in collecting examples from a region of high data uncertainty. But there's lots of reason to collect data from regions you haven't covered before, because obviously that tells you something new. So models which can separate out the source of uncertainty are Bayesian ensemble models or prior networks, more or less. And basically prior networks are a form of emulation of Bayesian models, which we'll get to a bit later. So that was the source of uncertainty. Now to Bayesian models. And please forgive me for going a little quickly. There's a lot to get through, and I'd like to get to the end. So anyways, yeah, so please keep up. And again, if you don't understand, just ask. I'll gladly explain. There's no point of me rushing forward if people don't understand what's going on. Anyways, Bayesian methods. You should be very painfully familiar with this stuff. You have your prior over model parameters P of theta. You use Bayes' rule to induce P theta condition on the data. And then you can do Bayesian inference by integrating out the model parameters. And then you'll get your predictive posterior P of y given x star and d. This is your Bayesian predictive distribution, which you all sort of aim to get. But we can also, instead of just integrating out the model parameters, we can consider sampling sets of model parameters from the model posterior and considering the behavior of the ensemble of models which we can have. And obviously the behavior of this ensemble will be very strongly influenced by the properties of the prior. So let's consider what the entropy of the predictive posterior was. As I mentioned before, the entropy of a single model was data uncertainty. But because we've integrated out model parameters, the entropy of the Bayesian predictive posterior will be a form of total uncertainty. Uncertainty due to both lack of knowledge and inherent uncertainty in the data. And here, like, we can get a Monte-Carlo approximation. We average together all the models, divide by m, and compute the entropy. And this is the total uncertainty. We can also consider what happens if we measure the average uncertainty of our ensemble. We measure the entropy of each model in the ensemble, and then we average the entropy. So previously we had the entropy of the average. Here we have the average entropy. And because each model in the ensemble is just a single model, and each model captures an estimate of data uncertainty, the average entropy will be the average level of data uncertainty predicted by the ensemble. Now this can sometimes be the same as total uncertainty, and sometimes it is not the same as total uncertainty. And the difference is quite interesting. So if the models are all consistent, if all the models in our ensemble are giving us the same prediction, then obviously the average entropy is the same as the entropy of the predicted posterior, and the difference will be 0. If the models are giving something very different, they're giving very confident predictions but of very different classes, then when we average together these predictions, we get a very high entropy posterior, but the entropy of the individual models will be very low. And therefore, the difference of the entropy of the average and the average entropy will be non-zero and greater than 0. And in general, this difference is always greater than or equal to 0 and is a measure called mutual information. Now, there's some math there which doesn't really matter. We don't care about it. The point is, this will be an estimate of Bayesian model uncertainty in the predictions, this difference. And if we have chosen a good prior, it will be a good estimate of knowledge uncertainty. So Bayesians often say that that model uncertainty is epistemic uncertainty. That's a little incomplete. Model uncertainty can be knowledge uncertainty or can be epistemic uncertainty given a good prior. But if I explicitly misspecify my prior, then it'll be a bad estimate of knowledge uncertainty. Anyways, so this decomposition is very useful, and it's nice to have. And it allows us to separate out the uncertainty in our predictions into knowledge uncertainty, like situations when we get out-of-domain inputs, and data uncertainty. Sort of math is nice, but let's go to pictures, because pictures give people intuitions. So here we have our prior plus data gives us posterior. We sample a bunch of models, and here are all the models in our ensemble, and this is our predicted posterior at the end. And here we have a confident prediction. All the models are giving us the same thing, and therefore the entropy of the average and the average entropy will be the same. The ensemble is consistent. We are confident in our predictions. It's all good. Suddenly, we give an input from a region of highly overlapping classes, and all of our models agree on a really high entropy distribution. So the entropy of the predicted posterior and the average entropy is the same. Difference is 0. We have no knowledge uncertainty, but we have a high degree of data uncertainty in our predictions. And finally, third situation, we give our model something it's never ever seen before. We have a well-chosen prior, and we get a very diverse ensemble of models. This ensemble gives us very diverse predictions for the same input, and the entropy of the predicted posterior and the average entropy of each model in the ensemble will be different. And therefore, that measure called mutual information will be high. Why is this called mutual information? It's because when it is high, we can identify which model made which prediction, as in each model is making a unique and identifiable prediction, which is not the same thing, which is not the case for the previous two examples. Is this clear? Any questions at this point? This is very important for us to continue.
Could you repeat please about mutual information?
So mutual information is a measure of statistical dependence between two parameters, the model parameters and the prediction. When mutual information is 0, the information about the model doesn't tell us anything about which prediction happened, and vice versa. Information about the prediction doesn't tell us about which model made the prediction. When mutual information is high, each model is making a unique prediction. Therefore, knowledge of the prediction tells us which model made it, and knowledge of which model made a prediction tells us which prediction it is. Right? So here we can identify that model 1 is predicting class 1, and model 2 is predicting class 3, and model 3 is predicting class 2. Yes?
So what we're seeing here is that for an outlier, each model is confident but differently.
Yes. You get people. Okay, let's say I get a bunch of school kids, and I ask them, what's the price of Bitcoin tomorrow? And they all disagree because they don't know anything about Bitcoin. They're just guessing wildly, and they'll give you different predictions. Now I get you a bunch of Bitcoin evangelists, and I ask them, what's the price of Bitcoin tomorrow? And they will all agree that it's super high, like $10 billion. And they all agree. Now, let's say they're right because they know Bitcoin and it actually is $10 billion, but whatever. So the idea is that when you get an ensemble of experts and they'll make different predictions, it means that basically the ensemble is exposed to something new and unfamiliar. So, right. We can also display the situation as points on a simplex, right? There we have basically, so everybody knows what a simplex is, right? Right. It's a space where all discrete distributions exist. So for the same input, we can imagine that each model gives us a discrete distribution over classes, and the ensemble's predictions are a bunch of points on the simplex for the same input. Right? So when we're confident, it'll be a tight cluster of points at some particular corner. When we are data uncertain, it'll be a tight cluster of points at the center. And when our models disagree and give us unique predictions, it'll be like a bunch of predictions all over the entire simplex. This is the sort of the ideal behavior we want from our ensemble. So we would like to choose priors and stuff which gives us this behavior. This is Bayesian uncertainty. This is classical or ensemble uncertainty. Now,
Which behavior?
sorry? This behavior.
The last one.
All of them. When we are confident, we want this. When there's data uncertainty, we want this. When we have high knowledge uncertainty, we want this. Right? We want an ensemble which displays these three behaviors in those three scenarios. Confident predictions, known unknowns, unknown unknowns. Right, now this is all great, and it would be good if we could ideally calculate all these measures in closed form. But unfortunately, Bayes' rule is intractable for neural networks, and approximate inference is also, like all the expectations are also intractable for neural networks. So you have to use various forms of approximations. So you can either use various forms of variational approximations, get some kind of variational posterior and get some variational estimate of the measures of uncertainty, or you can get Monte-Carlo estimates. Now Monte-Carlo estimates include Monte-Carlo Dropout, stochastic weight averaging Gaussian, stochastic weight averaging, and all those models. So I know Dmitry Vetrov works on this, on these kinds of like Monte-Carlo methods recently, and I think they're quite interesting. So anyways, so there's a bunch of, in fact, there's a bunch of different ways of doing this, and we're not going to look at any of them, except maybe the last one, the deep ensembles. So the point is there's many different ways to get an ensemble. Some are Bayesian, some are approximately Bayesian, some are Bayesian only in spirit, like the last two. One is getting an ensemble of models trained using different random initializations. So we take 5 or 10 or 100 different neural networks. We do random initializations and just train all of them. And they will be quite diverse. It turns out that this last method, while being computationally very expensive, is actually pretty good and quite simple. Doesn't require anything complex to happen, and it just kind of works out of the box. So like any comparisons to ensemble methods in my work and any numbers you see later, we'll be using this approach, unless I otherwise specify. Many people like Monte-Carlo Dropout. I personally very much don't like it. Anyways, but that's a little aside. Right, anyways, so like I said, it's hard to guarantee the diversity of ensembles because it's hard to pick the right prior. Furthermore, it's hard to pick the right inference, approximate inference scheme. Furthermore, the combination of your prior, your approximate inference scheme, your data, your architecture, whether you've got res nets, dense nets, magic shuffle nets, whatever else, like it affects all this, and it's very hard to guarantee the behavior you want given all the different things going on in your model. If this was a simple linear model, we could do everything. Or if this was a Gaussian process, we could do this by picking the right kernel. But that's a non-parametric method. Here, it's hard to guarantee this. So we get to prior networks. And this is basically my work. I think that was on time. Did everybody get the ensemble bit? Hopefully. Right, prior networks. So we said that an ensemble of models can be represented as a bunch of points on a simplex. Right? Basically, each model gives us a discrete distribution. A discrete distribution is a point on a simplex. An ensemble is a set of discrete distributions over classes, conditioned on the same input. And we can imagine that our ensemble, sampled from the model posterior, is in fact a set of discrete distributions mu, sampled from some underlying distribution over discrete distributions. Important conceptual jump. We have previously sampled from a distribution of model parameters, but it's the same thing as imagining there is an underlying distribution over discrete distributions conditioned on your input, and sampling discrete distributions from that distribution over distributions. So we're introducing a higher order distribution. We're effectively inducing a higher order distribution by considering a distribution of model parameters. Here I'm saying let's not think of this mechanism, let's directly think of the underlying process. And this is true for all Bayesian methods, for all Bayesian probabilistic methods. we're sampling from some underlying distribution over distributions. This is what happens to the outputs. And this is really the only thing it turns out we care about. At least that's what I think. So mu, just for reference, mu is a vector of probabilities of each class. So mu is a discrete distribution over classes. Anyway, so we can imagine that this set of points, the ensemble, is sampled from this distribution over distributions for a confident prediction, for a prediction in a region of high data uncertainty, or for a prediction with a high level of knowledge uncertainty. And what we're going to do is, this is my work from last year, is we're going to take a model, take a single neural network, we're going to approximate this underlying distribution. And we're going to refer to this network as a prior network, because I picked prior network because it turns out that it parameterizes a prior distribution, but a better name would have been posterior networks, because it's really the posterior distribution. Anyways, I was going for a rule of cool. I was wrong. I apologize. Anyways, I apologize for the confusion. The point is, so we have this distribution over distributions parameterized by a neural network with a single estimate of model parameters, and we can, again, obtain the predicted posterior by integrating out the mu's. And we basically wanted to give us these three behaviors. Again, just like the behaviors of the ensemble, we want this distribution over distributions to give us these three behaviors. We wanted to emulate the ensemble. But as it turns out, the mechanism of how it does this is entirely different, but the same external behavior. We want to basically, given some training data D, we want to get a distribution of distributions and sample discrete distributions from it to get, for confident predictions, we want to have a consistent ensemble of models sampled from that, or a consistent ensemble of models with a consistent ensemble of high entropy models, or a diverse ensemble if we have out of domain inputs. Is this clear? Cool. Right. Again, so the ensemble decomposes uncertainty using mutual information between theta and y. Here we're going to be doing the same thing. We can do the same thing between mu and y. So basically, like prior networks aim to emulate all the possible behaviors of an ensemble, all the mechanisms of obtaining uncertainty and decomposing uncertainty. Right. Now, given appropriately chosen prior networks, given appropriately chosen output distributions, we can actually do all this in closed form. We can actually obtain analytical solutions for all measures of uncertainty without sampling, and they are exact, assuming that the model is giving us something sensible. We don't have to approximate anything. Right. Now, the primary difference is that the ensemble was controlled by the prior, was indirectly controlled by the prior, the approximate inference scheme, and all of its interactions with all the components of the models. Prior networks will be controlled by the choice of training data in domain, and as you will later find out, out of domain training data, and the choice of loss function. And one of the important things in my work for this year is that it turns out the loss function I used last year was wrong, because I was naive and I thought, anyways, we'll get to that. But basically, prior networks are controlled by loss functions and data, ensembles are controlled by priors and approximate inference schemes. The underlying mechanism is different, but the external behavior should be the same, or we want the same external behavior. So how do we build one? So we're going to take a neural network, we're going to predict the parameters of a Dirichlet distribution. We're going to predict the concentration parameters alpha of this Dirichlet distribution. Right, and a Dirichlet distribution is a conjugate prior over categoricals, over discrete distributions, and we pick the Dirichlet because it is the conjugate prior, it has some nice conjugate properties, and because we can take all the integrals in closed form, take all the expectations in closed form, and obtain closed form expressions for all the measures of uncertainty and for our expected predictions. That's nice. So this is the Dirichlet distribution. It's just there for reference. You don't have to actually know what all that means. The important thing is the sum of all the alpha parameters. So alpha is a vector. Some of the components of that vector will be alpha 0, called the precision of the Dirichlet. The bigger the precision, the sharper the Dirichlet distribution is. It's like the opposite of, it's like the inverse of variance. And the expected predictive posterior of the Dirichlet will be given by the ratio of alpha for a particular class to alpha 0, to the sum of all the alphas. So alpha C over alpha 0 is our expected probability of class C. Clear? And it turns out that here that if you predict your alphas as just an exponent, it's basically the same thing as what your softmax gives. This will become a softmax. So basically nothing, so from the point of view of the predictions, nothing changes. What changes is that we now not only care about the relative magnitudes of our logits, we now care about also the absolute magnitudes of our logits. That's really the only thing which changes in our architecture. Right, so this is what we want. We'll use a multitask loss function. We'll have some loss, some in-domain loss, and we desire that it gives us a sharp distribution in one of the corners corresponding to the correct class, and we'll have some out-of-domain loss, where it'll predict a flat distribution over the simplex. This is what we wanted to do. The question is, how do we pick the appropriate loss function, and how do we get this out-of-domain training data? Those are the two things which really specify, as I said before, those are the two things which specify the behavior of our prior network. So, yeah, I really should have expanded this slowly rather than just giving it to you right away, but I forgot to comment out a line of code. Anyways, let's just start from the beginning. So we want to specify a target Dirichlet distribution p mu given beta, where beta are the target concentration parameters. Now, ideally, we would want a training set which contains x's and betas. Basically for every input, we uniquely specify a Dirichlet distribution. But we don't have this at all. What we have is the input and the class. We know which corner we should be sharp in, and that's the only thing we know. So the question is, how do we specify this Dirichlet? So what we're going to do is we're going to construct these betas by hand. These betas, basically the betas will parameterize the Dirichlet distribution. The betas need to yield the correct class. So the betas need to specify a Dirichlet which is sharp at the appropriate corner, and the betas need to reflect the level of a high level of confidence, or a low level of confidence, which basically means they need to be big or small. And all the betas need to be bigger than 0 because that's a mathematical requirement. So we're going to set them as follows. So beta c is a vector, and the components of this vector are as follows. So beta c is for the cth class. So a beta c the elements should be beta plus, where just beta is a scalar hyperparameter. The elements of this vector should be beta plus 1 if c equals k, if the kth element is the same as the class. So we'll have as many of these sets of concentration parameters as there are classes in our task. And if c is not k, we'll just have 1. Right. So if the hyperparameter beta is large, we'll have some sharp Dirichlet distribution near a corner, with the mode near a corner, which we desire. In fact, right in the corner, which we desire. If beta is low, we'll have a sort of a wide Dirichlet distribution. We'll have these things, right? So if beta is high, we'll have a sharp distribution in one of the corners. If beta is low, we'll have a wider distribution, which is leaning towards the corner. And if beta is 0, and therefore all the parameters are 1, we get a uniform Dirichlet distribution, which says that any discrete distribution is equiprobable, and we have highest uncertainty. Yes. So the vector beta c is a vector, and beta here is a hyperparameter, which we choose.
For each sample?
For each data set. So for in-domain, we'll have high B, high beta. For out-of-domain, we'll have low beta.
And for in-domain, let's say we have one beta for all.
Yeah, well, you just pick a big beta like 10,000 or 1,000 or 100, whatever it is. Right? And for out-of-domain, you just pick 0. So you specify a flat Dirichlet distribution. Right. Clear? Cool. Let's get going. So we have these three possible behaviors. Right. So which loss functions can we consider? So given this specified concentration parameters, which loss functions can we consider? And so we can, the first thing we can do is just consider the forward Kl divergence. We have a model which specifies a Dirichlet, which have a target, which is a Dirichlet. We know the class. Why don't we minimize the Kl divergence between the model and a sharp Dirichlet at the appropriate corner of the simplex? This is what we did initially. And in my naivety, and because we didn't check, we thought this was the correct thing to do. I will show you today that actually the bottom thing is the correct thing to do. The bottom is the reverse Kl divergence between the model and the target. Now, so these are the two Kl divergences. Forward Kl divergence is the expectation with respect to the target of the log differences, or the difference of the logs of the two distributions. While the reverse Kl divergence, which often appears in variational inference schemes and VAEs, is the expectation with respect to the model of this difference of the log likelihoods, right? And the forward Kl divergence, the standard Kl divergence, has the property that it's zero avoiding. Wherever the target is non-zero, we try to fit the model to the target, which basically means that we can have over wide distributions. While the reverse Kl divergence is zero avoiding. If you have a multimodal target, it'll pick a mode and sit on it, while the forward Kl divergence will try to sit on all the modes. Right. So basically, this is the analysis which we should have done. It's literally 3 lines, and we're a bit stupid that we didn't do this last year. But basically, if you consider the expectation of the forward Kl divergence loss with respect to your empirical data distribution with your underlying training data, then you can see that using some rather simple math, that you're actually minimizing the Kl divergence to a mixture of Dirichlet's. So if for some input you have a high entropy predictive posterior, you will have a mixture of Dirichlet's as your target. Basically, you get this if you have a high entropy posterior in your training data. Therefore, your model will try to sit on all the modes and then will invert the Dirichlet. Our target is this. We end up getting this inverted behavior, and this is what we actually wanted, but we didn't get, right? And this kind of is a pathologically bad behavior. The ensemble doesn't do this, and we don't want to do this either. Furthermore, it reduces classification performance. Last year, we had to use lots of extra auxiliary loss functions, like cross entropy, to get it to give good classification performance. Without it, it didn't. Furthermore, it doesn't scale to datasets with more than 10 classes. It's very hard to train this. And this is why we didn't test on things like CIFAR-100 and so on and so forth. We just couldn't get it to train. And we couldn't figure out why. But then at some point, I actually decided to do this analysis, and I figured out. Anyways, now let's consider what happens if we do the reverse Kl divergence. It doesn't really have much to do with zero avoiding. It doesn't really have much to do with the zero forcing nature. It has to do with something else. In the previous case, in expectation, we induced an arithmetic mixture of Dirichlet's. However, because we have reversed the order of the logs here, when this sum with respect to this expectation with respect to the empirical distribution of data goes into the log. Under the log here, it becomes a product of Dirichlet's. And a product of Dirichlet's will be plus a constant, which we don't care about because we're doing argmaxes over the parameters, is equal to a single Dirichlet whose parameters are an arithmetic mixture of the parameters of all the individual Dirichlet's. So what we get what we get now is still a Dirichlet distribution. It is a unimodal distribution. We get a product of Dirichlet's. We get a geometric mixture. Forward Kl divergence induces an arithmetic mixture. Reverse Kl divergence induces a geometric mixture. And a geometric mixture of Dirichlet's is a Dirichlet, plus some constants, which we don't really care about. So this is nice. We basically can induce the correct... Ideally, we don't actually want to be sharp at a corner. We want to be sharp at a point which corresponds to the correct level of data uncertainty in your data. And this way, we can induce the correct level of data uncertainty. And this is our target in expectation induced. This is what our model will learn. So our model learns the right behavior. And in fact, which I don't do here, but you can actually show that the reverse Kl divergence criteria actually can decompose into a reverse Kl divergence between the model and a flat Dirichlet plus a predictive term. It becomes a very elbow-like expression, but for completely different reasons. Elbows, like expected lower bound approximations, are used when you can't actually get the likelihood. Here we can get the likelihood, but it turns out that this reverse Kl divergence has an elbow-like decomposition and therefore similar elbow-like properties. We can balance together the prior. If we have a higher weight on the prior, you get a wider Dirichlet. If you have a lower weight on the prior, then that weight on the prior is controlled by beta. Anyways, I don't show this here because it's sort of tangential to the discussion, but you can find this in my paper, in the camera-ready version of the paper, which I haven't uploaded yet onto archive. Anyways, so this is what we get in the end. This is the appropriate loss function. we'll have some loss with respect to the parameters in the training data. Beta in is our in-domain hyperparameter, beta out is our out-of-domain, and gamma is the weight. What is interesting is because of the reverse Kl divergence, if we have some samples here which are sort of on the boundary, our target will also be a Dirichlet, where the hyperparameters are averaged between beta in and beta out. And that averaging is controlled by gamma. So if we use the reverse Kl divergence, we're always working, our target is always, in all cases, a Dirichlet distribution and expectation. Which is nice, because previously it wasn't the case. We're having various arithmetic mixtures and it was all going a bit wrong. So I said that we need a loss function. We found the loss function. Now we need the out-of-domain training data. We can do two things. We can just use a different data set. So like, let's say you're training on CIFAR-10. You can use CIFAR-100. Or you can scrounge the internet for extra training data and use that as your out-of-domain training data. Or you can use adversarial attacks, as we'll later see. And that leads to some interesting effects. Right. So but some of the properties of the training data we would like is that of the out-of-domain training data. So here we have the 3 red clusters. That's our in-domain data, and green is our out-of-domain data. We don't need to cover the entire out-of-domain space, because that's infinite and there's infinite variations of what is out-of-domain. What we need is to simply get a thick ring of data which isn't too far, it isn't too close, but is tight, like in the third picture, around our in-domain region. So we learn a tight decision boundary between the in-domain region and out-of-domain. So we are using data to tell the model where is the limit of its knowledge. In Bayesian methods, we used we built on prior knowledge. Here we used data to build a knowledge. And that's really the only 2 ways you can build a knowledge, priors or data. Yes?
Why is it good to use such kind of out-of-domain data? Why is it good?
Good because we can get a single model. We can explicitly control its behavior. So getting out-of-domain training data is not trivial. It is an unsolved problem. But in general, it can give us, it's like, so I think a nice comparison, and data, the experiments later will sort of show, that ensemble methods are like a broad spectrum antibiotic. They're pretty good for many things, but they're not perfect for anything. Prior networks are like a targeted thing. We can learn a very specific form of out-of-domain. We can learn a very specific form of out-of-domain distinction, and it'll be very good, much better than an ensemble method. But there may be forms of out-of-domain data which are not covered by this training data, and therefore it'll do badly in these cases. So different models, good for different things in different situations. But one of the benefits of a prior network is that it is much faster than ensemble. You have just one model. You have analytic expressions for uncertainties. You don't need to approximate anything. The only thing you need is the appropriate loss function, which we found, and some training data to build in knowledge about limitations of knowledge.
Then you say that prior networks are better than ensembles
in some cases. Sorry.
Do you mean then that do you use OD data to train ensemble or not?
No. Because the ensemble, it's different. The ensemble has multiple models. Prior network is just one model.
Yeah.
Ideally, the ensemble's behavior, both are forms of an ensemble. One is an explicit ensemble, an ensemble is a bunch of samples from a distribution over distributions. A prior network is a distribution over distributions. We have different mechanisms of controlling its data, its behavior. Now, an ensemble explicitly has multiple sets of model parameters which can agree or disagree. You can use bootstrap, you can use random initialization, you can use bootstrap, random initialization, and swag on top of every together.
If you use OD data to train your prior network, then your prior network will be better for this OD data.
Of course.
But maybe you can
And
use OD data for training ensemble, and then ensemble will be better.
Not, I think it's really hard.
For 2 models. It's not very.
There's 2 different mechanisms, right? So sure, you can, how would you train your ensemble on OOD data?
Different question.
See, that's a different question, and it'll be very expensive to train your ensemble on OOD data, right? I could imagine what you could do is you could train a prior network, and then you can make an ensemble of prior networks, and combine the benefits of both approaches, maybe. That's one thing to do. I haven't done that, but basically, there's 2 different ways of building in prior knowledge. One is priors implicitly, which gives us different models. The other one is data explicitly. And I think it's a fair distinction. Anyways, so this is what. So here we have. So here we trained a prior network using the bad forward Kl divergence loss function, and we've decomposed its measures of uncertainty. And here it all just has gone. So we use this basically this data here at the end, and it's all gone bad. Here total uncertainty is high when 3 classes overlap, when 2 classes overlap, and out of domain. Data uncertainty doesn't show any structure; it's just flat and uniform in domain. And knowledge uncertainty, it has this weird, I don't know, string structure, whatever. If we use the forward Kl divergence, the reverse Kl divergence, we actually get the structure we want. We have high total uncertainty where 3 classes overlap, lower total uncertainty where 2 classes overlap, and again high total uncertainty out of domain. So this shows the right structure of total uncertainty. This shows the right structure of in-domain data uncertainty. Actually, like in-domain data uncertainty will be the structure of uncertainty in domain, and out of domain. And knowledge uncertainty is low in domain and higher out of domain. These are the behaviors of our measures of uncertainty, which we want, and we can show that it all works quite nicely for that. Right here, I basically trained prior networks using the forward and reverse Kl divergences on CIFAR-10, CIFAR-100, and Tiny ImageNet without any out-of-domain training data. This is just using a different loss function to train a DNN on in-domain data. And we have an ensemble. We can see that basically a DNN, like a standard DNN trained using standard cross-entropy, has about the same error rate as a prior network trained using reverse Kl divergence. And I think the slightly better error rate is due to the smoothing factor of making sure that the alphas are always equal to or bigger than 1, right? While forward Kl divergence gives us a much higher error rate. And we couldn't get it to train on CIFAR-100 or Tiny ImageNet at all using forward Kl divergence. We can only get it to work, but we can get it to train using arbitrarily many classes. Well, here only up to 200 classes, but in principle it can go higher using reverse Kl divergence. So it's all fine. Now, a benefit of ensemble approaches is that when you average together the ensemble, you get improvements in the classification error rate. And this is a benefit of ensembles, which prior networks do not share in their current formulation. I've done something different. My sort of ICLR paper is where we try to distill ensembles into a prior network, but that's slightly different. Yes? No, this is a deep ensemble. We just randomly initialized many networks, and we trained using those. You can sort of imagine that they are sort of Bayesian, but not quite. They're actually map estimates, so they're not quite Bayesian, but they have the same. So you can be Bayesian in 2 axes. You can work with multiple sets of model parameters or a single set of model parameters. So deep ensembles are Bayesian in the multiple models kind of axis, a binary distinction. And then there's how accurate your approximate inference scheme is, and obviously for random init ensembles, you have a very bad approximate inference scheme. Yeah? Of course, you actually parameterizing a posterior over distribution. You actually have a posterior distribution over distributions. I called it prior because it parameterizes a Dirichlet distribution, which is a conjugate prior. But it's really a misnomer. It should be called a posterior network. It's completely fair. Why would it not be fair? Well, I tried dropout, and dropout was much worse. It didn't give us. I'm comparing with the better ensemble, and a deep ensemble is, like in my experiments, has always been uniformly better than dropout in terms of accuracy, in terms of measure of uncertainty in all tasks. Deep ensembles are better than dropout. I haven't tried swag, and I think swag would be interesting. I just haven't had time to do it. But I think even in the swag paper, there's a comment somewhere in the appendix that like deep ensembles are interesting, but we don't compare because it's not Bayesian. So. Anyways, but don't quote me on that. There's something to that effect. So anyways, ensembles are cool because they give us better classification performance, but prior networks using reverse KL are not any worse than standard DNN. So it's all fine. While forward KL is the bad loss function, which we naively tried last year. So now here we're doing out of distribution input detection. We're comparing using area under an ROC curve. Here we trained prior networks with CIFAR-10 in domain, CIFAR-100 out of domain, and here we're testing on different held out of domain test sets. We're trying to find a distinction between the CIFAR-10 test set and SVHN, Elson, or tiny ImageNet test sets. And we're assessing the area under an ROC curve, which is basically a summary statistic for threshold-based outlier detection. It's a plot of false positives versus true positives. Anyways, higher is better. So here we see ensembles are pretty decent. Prior networks using reverse KL are actually not too bad, and prior networks using forward KL are not too bad, and prior networks using reverse KL are pretty damn good. They're the best here. Here, we couldn't get prior networks using forward KL to train. Here, because we trained a model on CIFAR-100 using tiny ImageNet as the held out data. And here we can see that a situation where ensembles do better. So ensembles are like a broad spectrum antibiotic. They're pretty good for everything, but they're not perfect for anything. Here we can see that by training on tiny ImageNet, for some reason we've decided that Elson, we can perfectly separate out Elson, and we can separate out SVHN better than an ensemble, but we can't separate out CIFAR-10. Using a prior network, we can separate out, we can better separate out CIFAR-10 using tiny ImageNet.
Some intuition about why does it happen?
Of course, because when you're using, tiny ImageNet is far more diverse and weird than CIFAR-10, and so if you're learning a distinction between CIFAR-100 when you're learning a distinction between CIFAR-100 and tiny ImageNet, CIFAR-10 is actually really close to CIFAR-100, and you will learn a two loose decision boundary. So you have, I think the situation is actually like this. You actually have case one.
Okay, but
intuitively.
Prior networks just much better, obviously, and it's interesting why it's so better than.
Because you have explicitly built-in knowledge. I mean, I'm sure I can find data sets where it won't work well. And as you consider more complex tasks with more classes, with fewer examples, with fewer training examples. Here we have 10 classes, 50,000 training examples with 5,000 per class. Here we have 100 classes.
And do you also use kind of out-of-domain data for training ensemble?
No.
Pure ensemble?
No.
Okay, maybe it's interesting to see comparison when you train ensemble.
How would you train the ensemble on out-of-domain data?
You can just, I don't know, maximize entropy.
So then you'll be basically doing a prior network, an ensemble of prior networks. So models which, there's a class of models which maximize the predictive entropy for out-of-domain data. Prior networks are a strict generalization of such models. And if you just look at the entropy of the predictive posterior for prior network, it'll be exactly the same as these models. So if you train an ensemble of models where you're maximizing entropy for out-of-domain data, you effectively have an ensemble of prior networks. It'd be an interesting thing to do. I haven't tried. I think it's actually worthwhile looking into.
Because it's not too fair right here. Because one model that was trained with out-of-domain data and another model that was trained with no out-of-domain data.
No, but I disagree about the fairness. You have two different mechanisms for building in knowledge about limitations of knowledge. You could conceptually have selected a very good prior and sampled an ensemble which is highly diverse. So imagine you have a Gaussian process. You can select a kernel such that far away from your training data you get really high variance, right? You have no out-of-domain training data there, but you've picked the right kernel, you've picked the right prior over functions, and you have a Gaussian process is a distribution over functions. If you had also predictions of heteroscedastic variance, it'll be a distribution over distributions. But a Gaussian process is a non-parametric method which is able to do something like this.
Okay, let's discuss it later.
Sure.
Sorry,
Yeah.
what measure of uncertainty are you using here?
Here I'm using mutual information, so knowledge uncertainty.
I see, yeah. And what if you use total uncertainty for measure?
I have those results in my PhD thesis. Basically, for different tasks, different measures of uncertainty are actually good. For the task of alpha distribution input detection, measures of knowledge uncertainty tend to be strictly better than measures of total uncertainty. For tasks like error detection, measures of total uncertainty are better because you don't care why you've made an error, you just care that you've made an error, and therefore total uncertainty is better for that task. So, yeah.
Could it make any sense to use not the Dirichlet distribution, but any other, imagining that despite it being not conjugate, it's technically
Yes, no, so
like, for example, multimodal,
like a mixture of Dirichlet's.
for example.
Yeah, sure. Yes, sorry, it would make sense in a different context. So my recent work is something called ensemble distribution distillation. I don't really talk about it here, but in ensemble distribution distillation, so one of the things I don't show here, so one of the things you've noticed is that ensembles have higher predictive performance. One of the things I don't talk about here is misclassification detection, but ensembles also do better than prior networks for misclassification detection. I don't mention it here because it's strictly a discussion about loss functions. But anyways, ensembles are better than prior networks for misclassification detection, and they're better at prior networks at just predictive performance. So an obvious question is, can we somehow combine prior networks and ensembles, considering that a prior network is a model which can emulate an ensemble? So what we did is try to distill an ensemble of models into a prior network such that the Dirichlet captures the diversity of the ensemble. Now, obviously, in this case, the Dirichlet may be too restrictive, because the ensemble may not be Dirichlet distributed whatsoever. It could be something really weird on the simplex. And in this case, you may want to consider more flexible forms of distributions on the simplex, like mixtures of Dirichlets, like logistic normal distributions. Sorry, logistic normal distribution, or the generalized Dirichlet distribution, or there's others. But yeah, it's an interesting investigation. Here, I just consider Dirichlet because it's just nice, simple, easy. It's like the Gaussian for categorical data. So, anyways, so long story. These are the results. TLDR, reverse Kl divergence, is the way to go, and we can train on more interesting data sets. I've also trained, don't show here. This is some of the experiments I've been doing recently. Is I've trained a prior network on tiny image. So tiny ImageNet is a 200 class subset of ImageNet. So if you take a different non-overlapping 200 class subset of ImageNet and use it as out-of-domain data, you will actually be very, very good at detecting all the other held-out subsets of or classes of ImageNet, for example. But so it generalizes to more classes. It generalizes to bigger data sets, and it's not slow. Ensembles ensembles are cool, but ensembles are strictly, if you have m models for inference, your inference is m times as computationally complex, which is one of the bad things about ensembles. Anyways, so yes. Finally, and this is the part which I sort of put together in like a day, and it may be a bit more rickety, is adversarial attack detection. So I'm sure you've all heard about adversarial attacks. These are minor perturbations of the input which cause strong changes in the prediction. So you have a picture of a panda plus some adversarial noise. It tells you it's a giraffe, and it's very confident about it being a giraffe. Now, these things have, so you can make adversarial attacks in many modalities, for images, for text, for audio. For example, for like Siri or for Alice. I don't know if people have tried this for Alice, but I think people have tried this for Siri. Is that if you have a little background noise, like some noise, you can actually do different things. So you can adversarially attack Siri, for example. Adversarial attacks transfer. If you construct adversarial attacks against one model, you can actually attack a different neural net with it as well. And you can also make them in the real world. I can make a sticker, I can put it on my hat, or on somewhere on my chest, and there's a car coming towards me. It's controlled by a neural network, and it'll do something weird. Anyways, so there's a security concern. And the question is, can we use uncertainty to detect adversarial attacks? So what is a typical adversarial attack? We want to generate an adversarial x tilde such that it affects the prediction and it is minimally different from the original image, the original natural image. So here we have so we can phrase this as an optimization problem where you have like this adversarial attack generation process. It's an argmin over this loss, which tries to attack the model in some way such that the solution is within some epsilon of a perturbation around the natural image, where this is typically L2 or L infinity or L1 or some other difference. Right? And basically, most adversarial attacks can be expressed as some form of optimization scheme. So this is my interpretation. People can disagree with this. But so this is a manifold of natural images. So the red points are your in-domain data like before. But now we're considering that our natural images lie on some lower dimensional manifold in a high dimensional space. Say this is the manifold of all possible natural images, right? And so here's your in-domain region and your out-of-domain data. Let's say in-domain your CIFAR-10, out-of-domain is your tiny ImageNet and CIFAR-100. It's still on the manifold. You still have natural images of real objects. So it still lies on the same manifold. And if you generate adversarial attacks, the stronger your adversarial perturbation, the more noise you have, the less natural your image, and therefore you leave the manifold. You go off the manifold. So adversarial attacks can be interpreted as off-manifold out-of-distribution inputs. And therefore, why don't we just treat them as out-of-distribution data and try to detect them using measures of knowledge uncertainty as before. So how do we detect? Let's define an adaptive adversarial attack. This is not just so typical adversarial attack is just one to flip a class. Here we have more constraints. We want an adversarial attack on an adversarial input such that its measure of uncertainty is less than some particular threshold, and such that it is a successful adversarial attack. So it actually flips the class. This means that it has flipped the class, right? This is our indicator. So an attack is successful if its uncertainty is low and it has successfully affected the prediction in the desired way, right? And then we can basically compute true positives, false positives, and we'll use something called the joint success rate, which is where true positives equals false positives, the equal error rate of the detection scheme to assess how good we are at both, how good an attack is at both affecting the prediction and evading detection. Right? So prior networks yield rich measures of uncertainty, and thus they greatly constrain the solution space of adversarial attacks. If you only care about detection using confidences, it basically means that you're putting a constraint on my solution has to be in some region where the class has changed and on the magnitude of just one logit. If you're using entropy of the predictive distribution as a measure of uncertainty, you're saying my solution has to lie in the region where it's misclassified and where the relative magnitudes, the ratio of the logits, are the same as for the in-domain region, for the natural input. And finally, if you're using things like knowledge uncertainty, then you're putting a constraint that your solution has to affect the prediction in the desired way, and also you're putting a constraint on the relative and absolute magnitudes of the logits. So you're just piling on constraints which your adversarial attack optimization process has to satisfy, which is why it's more complex. Now, furthermore, we can explicitly train our prior network to yield certain behaviors in certain regions, so we can try to generate adversarial attacks and train a prior network to yield the correct prediction and a high measure of uncertainty on those attacks. So what do I mean by that? Here we have so there's something called adversarial training, and adversarial training is you take your natural data, you take your adversarially changed data, and for all of them you try to predict the correct class. Effectively, you're trying to extend your decision boundaries correctly off manifold. Here we're generalizing that. We want the model to predict the correct class for both natural and adversarial data, but we also wanted to predict a higher measure of uncertainty for adversarially perturbed data. And this is a generalized form of adversarial training. Standard adversarial training just cares about the prediction. Here we care about the correct decision boundaries, but also a higher measure of uncertainty, such that if we see an adversarial input, we still make a good prediction, but we say, look, I'm making this prediction, but I'm really not confident here. Right, and this is strictly sort of more advanced than what we're doing with out-of-distribution data before, because previously we didn't know anything about the out-of-distribution data. We assumed it was all out-of-distribution. Here we know something about it. Here we know to which class it should belong, and therefore we can say make the prediction with the correct class, but a higher measure of uncertainty. Clear? And we were using again our reverse Kl divergence loss function. The only difference is that previously for out-of-domain the beta hyperparameter was 0. Here it'll be 1. We're basically making the least confident prediction we can, while also still having a mode, which leans towards the correct class. That's really basically it. And yeah, so the experiments which I show here is we consider Monte-Carlo Dropout, so using Monte-Carlo Dropout on a particular net to compute mutual information. because simply it was easier to attack it was easier to do all the computations for Monte-Carlo Dropout than like 10 different networks in different files. And we're also using standard adversarial training. We also combined Monte-Carlo Dropout with standard adversarial training just to see what would happen. Our prior network is trained on one-step fast gradient sign method attacks. Really simple, cheap to compute adversarial attacks which are generated dynamically in training. And we evaluate on strong adaptive whitebox attacks which are iterative. So these attacks attempt to affect the prediction and switch to the target class, and also to yield the same measure of uncertainty as the natural input, such that it's impossible to distinguish between the natural input and the original input. And we can and they do multiple steps of gradient descent, and therefore are much stronger. Right. And we've done this experiment on CIFAR-10 and CIFAR-100. So this is the results. So this is the joint success rate, how successful the adversarial attacks are. On top you have standard DNNs, Monte-Carlo Dropout DNNs, DNNs with adversarial training, and Monte-Carlo Dropout DNNs with adversarial trainings, and finally prior networks here. We can see that basically, like, while I think if we continue doing far more iterations, we'd eventually get to the top somewhere maybe here. But the point is, we've made it far more computationally challenging to find a successful adversarial solution such that it flips the class, such that it affects the prediction, and also is undetectable. So here we can either detect it, even if it flipped the class, or it doesn't flip the class well. It doesn't. We've constrained the solution space. So basically, and this is because prior network adversarial training is a drop-in replacement for standard adversarial training. This is nice, because standard adversarial training clearly doesn't do well against these types of attacks. This is what happens for CIFAR-100. Not as well. You have more classes, fewer training examples per class. So you have basically more decision boundaries to flip, and so on and so forth. There's more solution spaces. Therefore, it's harder. But it's still much harder to attack a prior network than all the baseline models. So this is nice. This shows that we can use prior networks trained in an adversarial fashion to make models more robust against adaptive white box attacks, the most challenging type of attacks, which are aware of the detection scheme, are trying to actively bypass the detection scheme and also affect the prediction. And yeah, this is a nice benefit of prior networks. That's about it. Thank you. Yeah, any questions?
Are there any other methods that also use out-of-domain data when training, like during training, to give better estimates of out-of-domain uncertainty?
So there's a work by Lee, and some guy else, by a bunch of Koreans, which basically did the same thing with entropy, and prior networks are a strict generalization of that model. So their model could only really predict total uncertainty, and you couldn't decompose uncertainties. Prior networks are able to decompose uncertainties. Yep?
Speaking of the regression problems,
Yes?
how you can solve the
So this is actually like this is a really sad thing for me. So in my thesis, I wrote about prior networks for regression, but I never ran any experiments. So prior networks for regression would parameterize a prior distribution over normal distributions. So you have a probabilistic regression. You have a standard probabilistic regression model would give the parameters of a normal distribution. So you have continuous targets y, and you have and your model predicts a distribution over continuous targets y. So a prior network would predict a prior distribution over normal distributions. This is something called a normal inverse Wishart distribution, or a normal inverse gamma distribution, and it gives the parameters of this. Now, because I've had a really busy summer with like thesis, defense, and everything, I just wrote about this model in my thesis and hoped to make an ICML submission. But somebody was faster than me and made an ICLR submission about the same thing this year, except they train it in a different way. So they consider basically what a prior network is. They consider a model which predicts a higher order distribution over lower order distributions, which is basically a model which works with distributions over distributions for regression, but they train it in a completely unrelated fashion, using evidential ways, which are this like alternative ideological formalism, and they have interesting results. Yes.
Actually, the second question in the same way. Am I right that the visual information in a continuous setting is unbounded.
No, mutual information is bounded. Entropy is not. So if you compute differential entropy, I mean, like if you like look, if you have just a normal distribution, is differential of just a standard normal distribution, is differential entropy will be log of the variance multiplied by a constant plus a constant, right? And you can have an infinitely small variance, and therefore your log of variance, minus log of variance, therefore you have a very low uncertainty. Maybe I dropped a minus sign. Basically, your differential entropy will be proportional to the log variance. And if your variance is very small, your differential entropy will be tiny. And if your variance is infinite, then your differential entropy will also be infinite. So differential entropies are the sort of equivalent of entropy for continuous probability distributions. But because continuous probability distributions, you can make relative statements. Like for example, for this prediction, my differential entropy is bigger or smaller. And relative differential entropy is just Kl divergence, which is bounded from below. But you can't make absolute statements. You can't say, well, like my differential entropy is so and so I'm so and so uncertain. You can make absolute statements for discrete distributions.
Why I'm asking about it is because some of active learning techniques tries to maximize the epistemic uncertainty in some way, and if it is unbounded from the top.
Well, mutual information it's unbounded from the top, yes.
Yeah.
Mutual information is a Kl divergence, and Kl divergence is unbounded from the top, yes.
So the question is, it okay to make this?
So one thing you could do, you can sort of bound it. You can say, look, my conditional. If I have just the distribution over y, p of y, it'll have a higher differential entropy than p of y given x. So let's specify my upper bound as the average differential entropy of the marginal distribution over y, and that'll be sort of bigger. And I think you can work with that.
Another question.
Hmm?
Have you played around with models that use logistic normal distribution instead of?
No, I have not. I'm curious to do that. Haven't really had the time. I think logistic normal distributions are really weird and very kind of interesting. They can be, they can draw really weird stuff from the simplex.
Yeah.
But I think you can't get the moments of it in closed form. So I think you might have issues in computing measures of uncertainty and taking expectations if you have logistic normal distributions. I think you will need to do sampling. I mean, it'll be cheaper than doing Monte-Carlo sampling of models because you don't need to run the neural net. You only need to evaluate the neural net once. But I think sampling from the logistic normal distribution might be difficult in itself, maybe.
I'm asking because I saw this in paper by Kendall and Gall that was published in mid-2017. They basically do this for classification, I think. So they train this logistic normal model, and they use sampling. And I think the similar thing could be tried with prior networks. So you could have something like your artificial Dirichlet priors,
Sure.
but for logistic normal.
But okay, you could do this, but what's the point? What is the advantage of the logistic? Given the knowledge you have, given that your training data is only x and y, and here I'm only setting one hyperparameter, which is the precision, what is the advantage I can get from using a more expressive distribution? And I'm not sure it's clear. So when you're doing things like ensemble distribution distillation, where you have an ensemble of models and they may be distributed in some really strange way, and you're trying to distill that into a single prior network, I think there it very much makes sense to use a more expressive distribution. But I'm not sure if you're just treating a classical prior network that it makes the same amount of sense.
No more questions? Let's thank the speaker.
Cool. Thanks.